We're going to now take a look at how we can solve some problems involving polynomials. Because the multiplication of binomials can be related to the area, we're going to start there. So we have a rectangle with a smaller rectangle within it, and we're given the dimensions. So the large rectangle has a length of 5x minus 2 and a height of 2x minus 1. The smaller rectangle has a length of x plus 3 and a width of x minus 1. We have to write an expression to represent the shaded area. So if you take a look at this, we can see that if we were to find the area of this large rectangle here, and then we can remove the area of that smaller rectangle, and that will leave us with the area of just the shaded region. We know that we can find the area of a rectangle by multiplying the length by the width. So our length is that 5x minus 2 times our width of 2x minus 1. And then our smaller rectangle has a length of x plus 3 and a width of x minus 1. So now we're going to begin by getting rid of those brackets. We're going to multiply those two binomials together, and then we're going to multiply those two binomials together. To ensure that we remember to multiply every term by every other term, we can FOIL this. So we're going to multiply the first terms. 5x times 2x is 10x squared. And then outside, minus 5x minus 4x minus 5x minus 4x gives us minus 9x, and then negative 2 times negative 1 gives us that positive 2. We're going to do the same thing, FOIL the second set of binomials to eliminate those brackets. We're going to leave that second one in brackets because we also have this negative that will get distributed into that bracket. So we're going to multiply that negative 1 in. We're going to combine our like terms together, and this is the simplified expression to represent just that shaded area within that diagram. In our next question, we have a square wading pool in blue here, and we also have a square deck that surrounds that pool. We have to write a polynomial expression that represents both the area of the pool and the pool deck. So what is the area of this entire piece here? Because it's a square, we know that the length and the width will be equal on both the pool and the deck. So we're looking for what this dimension is. We can see that we have 2 meters plus 2 meters plus this piece, and we don't know what that piece is, so we can go ahead and represent this section with a variable. We're going to choose P for pool. So we have P plus 2 is just P plus 4 when we combine those like terms together. And so then we have the same dimension on the width. We're then asked to determine what the area of that deck and pool is if we know that the pool has an area of 49 square meters. So if I know that this in blue is 49 square meters, I can now find that length P because I know that the area is just the side length squared. So in this case, we have P squared is equal to the area. The area we can substitute in is 49. And then if I'm trying to isolate P in order to get that length, in order to eliminate a squared, we can square root. And then what we do to one side, we do to the other side. So on the right-hand side, when I square root a squared, it's going to cancel out. And then on the left-hand side, the square root of 49 is going to be positive 7. Because this is a length cannot have a negative dimension. So we're going to take the positive square root. And then when we substitute that in here, so if P is equal to 7, 7 plus 4 is 11, 11 squared is 121. And then make sure that you include the appropriate units. So this is going to be square meters. In our last example, we have a rectangular piece of cardboard. We're going to fold along these lines here in order to create a box, and the box will have no top. We're asked to write the expressions for the dimensions of the box. So dimensions are the length and the width. So we can see that the length is 25 centimeters, but we have removed x and we have removed x. There's an unknown amount that we've taken off each side, and these two sides are equal. So I can go 25 minus x is the same as minus 2x. And then along the width, we have 20 centimeters, we've removed x, and we've removed another x. So the dimension for the width is just 20 minus 2x. The volume of the box, we know volume of a rectangular prism is just the length times the width times the height. We've got the length and we've got the width. Now the height, if we were to fold along this line and fold this piece up, the height is going to be that x, that unknown amount. So we can go ahead and substitute those values in. And then if we have to simplify this expression, we have a binomial times a binomial times a monomial. So we have 3 factors here. So what we want to do is start by foiling this out. So we're going to FOIL that out first. And then once we FOIL that out, we're going to distribute that x in. So even though it's over here, we're still going to multiply that into the bracket. And then we end up with this. We have no like terms, but we do tend to line the terms up in order of degree. So we're going to have degree 3 is the highest, then degree 2, then degree 1. And that is the simplified expression for volume.